let's come back. Okay, so before diving into the block layer, let me quickly go through how CPU access the peripherals. Okay, so because like usually in our system, CPU needs to access like the register, for example, in the SSD, so to do some management, or even to CPU to access like the keyboard kind of data inside the register, those kind of stuff. Okay, but how to do this kind of addressing things? So there are two ways. One is called port mapping, another is called memory mapping I/O. So this is a CPU. And like for port mapping I/O, because it is called isolated I/O, so it is about the I/O address space and memory address space. They are separated. Okay, so this is the memory address space and this is the I/O address space. Okay, so for example, if you are using a 32-bit systems, then the memory address space, like you're using a 32-bit to do the memory address. And then I/O address, you will depends on another address space. Okay, and if we are going to support this kind of isolated address space, we need extra instructions. So in this scenario, CPU use low store instructions to access the memory address space. Okay, and this is the directions that usually general CPU access the memory. But in and out, this is another set of the instruction. So CPU needs to support this in and out instruction to access the I/O device if they are going to choose for, if this CPU is going to access the I/O device in different address space, then we will need in and out instructions. Okay, so usually this case, usually we're used for this kind of like timer, interrupt controller, this kind of low bandwidth kind of device. Okay, so usually it's about, because if you are going to do this kind of stuff, you need extra complex management for this in and out kind of stuff. But you can save a little bit. You can save a little bit of the memory address. What I mean, memory address is about the address space. So kind of think about if you are using a 32-bit systems, then you can only address in 4 GB. So it doesn't really mean about how many DRAM you have now. It is about you have 32-bit for your CPU. So your CPU can only address up to 4 GB, and it can be, some of them can be in the DRAM and some of them can be in the I/O. So this case is called memory mapping I/O. So like this, if this is the 4 GB address mode, then part of it can be I/O address, part of it can be the DRAM. Okay, so I need to clarify here as the address space is not equal to the DRAM space. So address space is only for the CPU, how much of the address it can use to address it. And then this addressing, it can be DRAM or it can also be I/O. And this is called using the memory mapping I/O. Okay, and this one, if you have a 4 GB, then you have a 32-bit, then you can use a 32-bit to address the memory address space. And the I/O address, we will use another address space to address it. And because you are using another address space, so you need extra instructions. You need to let your CPU to support different instructions. And using the right-hand side memory mapping I/O, both of the I/O and memory address, you can use the low store instructions. So for example, if a CPU is going to access like NVMe driver stuff to access the NVMe SSD, and NVMe SSD inside there are several registers to do the control stuff, and the register will be mapped to this I/O address. So CPU with this I/O address can directly get the data from the register inside the NVMe SSD. So it is fast and you can increase the bandwidth. But the point is about if you are not using a 32-bit system, you need to sacrifice part of the address and use for this kind of I/O device. Okay, so this is about the memory mapping I/O stuff. Okay, so there is another concept is called like DMA. So DMA is about to transfer data directly between memory and I/O device without CPU's interventions. So what does this mean? So usually you have CPU and like you have I/O device and memory. Okay, so if you are going to get the data from I/O device, then who is going to keep track of moving progress. If there is no DMA, then a CPU needs to set up the range and move the data from IO to memory and then to monitor if it is finished or not. And then for the second IO, CPU needs to do it again and again. So CPU so using the CPU, actually, it will waste a lot of CPU time to monitor, to set up this kind of IO stuff. So a better way is to use a technical DMA. So DMA usually is a lightweight controller. It is also a kind of CPU, but it is a microcontroller. It is a micro CPU. So DMA is about like this. When we are going to move the data from IO device to memory, CPU will tell the DMA about, let me set up the range of the data you are going to move. For example, CPU will tell the DMA controller to say, hey, maybe let me move like 1 GB of data. And the starting point is from which address, and the offset, the length will be 1 GB. And then DMA will start to move. DMA will read out the data from the IO device to the DMA's register and then move it to the memory. So DMA will take care all this kind of moving stuff. And after CPU do the configuration on the DMA controller, CPU can do other stuff. Okay, CPU doesn't really need to wait here, doesn't need to wait synchronously for the IO completion. So CPU can just do any other stuff than waiting for the movement. Okay, so this is how DMA work. Okay, so just about to a proxy about to help CPU to move the data. Okay. Okay, so those are the like hardware part or the CPU part. So let's move back to the kernel part. So this is a split view of the kernel IO stack. So this is applications, and under here, those are hardware, right? So there are different hardware devices. There are keyboard, mouse, SAS, USB, PCIe bus, those kind of stuff. So for each of the device, actually, there are device controller here. So there are the keyboard device controller, mouse device controller, blah, blah, device controller. So anytime when you see a controller, it means like there is a micro CPU there. So a micro CPU there means we are going to run some software stuff like firmware. So keyboard device driver inside, it will run the keyboard firmware. Mouse device controller will run the mouse firmware, and a hard disk drive, SSD, those kind of controller, they will run their own firmware there. Okay. But the stuff is about then how the system, how the operating systems can interact with this kind of controller. Okay, how to send the request from the system into the hardware. So the thing is the device driver. So device driver works as a bridge between the operating system or our host systems and the device. Okay, so you can see like this, there is a keyboard device controller. So it means we also have a keyboard device driver. So device driver can talk to the device controller, or device driver can interact with the device controller. So for each device, there are more like mouse device driver, as the SAS device driver, USB device driver. So different device driver can talk to their related device. Okay. And then device driver is also part of the operating system. Okay, so device driver is part of the operating system because device driver is also a kind of the kernel code. Okay, and firmware is not a kernel. It's not in the kernel. So firmware is inside the device. So firmware is not a part of operating system, but device driver is part of the operating system. And there is let me check. I think I didn't put it in the slides, but there is a very interesting analytics data here. Like I think it's kind of 70% of the Linux OS source code, they are about device driver. So like your scheduler, your memory manager, your CPU scheduling stuff, actually there's less than 30%. But device driver, because there are a lot, each device, they have their own device driver. And then maybe not only one device driver, maybe they have two, because you have a NVMe driver, you can have the PCI driver, you can have the SATA device driver. So there are way more device driver you think in the OS kernel. Okay. Okay, but yep. For the device part, actually, we split into two kind of devices according to their characteristics. One is called block device. The other is called character device. So block device is addressable in device-specific chunks called blocks. Okay, so it is more like this kind of stuff. Just like if this device is going to get more data, like more sequential data, or like more a bunch of data from a device, it works like the block device. So just like your hard disk drive, usually when you are going to read the data from a hard disk drive, you are going to read out a bunch of data or a block of data, right? So because like your file is in the like 2 megabyte, 4 megabyte, or even 1 gigabyte. So usually you are going to ask for a block of data, and there is called block device. So like CD-ROM, storage device, they are all block device. Okay, so because you are going to read out a block of data, so it is possible for you to do the seeking. So you are going to read maybe in the middle of this block or like in the head of this block. So you can, so block device also support like random access. Okay, and in most cases, block device, they are mounted as a file systems. So like if you have a hard disk drive, then you will mount a file system on this hard disk drive, like this kind of stuff. Okay. Okay. So yeah, I think data blocks we'll talk about it later. So it doesn't really need to talk now. So here is about USB driver and SAS drivers. They are all block device. So how about character device? So character device providing access to data only as a stream. So what do I mean for stream? For example, when you are using a keyboard and you type something on a keyboard, you type like A, B, C, D, and then it is a stream because the first one is A and then B and then come also like C and D. So they are usually in the bytes granularity. Okay. And also the mouse, how often you click the mouse, this kind of stuff. So they are all about the character device. So the thing is about if the data you are going to access is in a block, like continuous, like 512 byte, this kind of size, then it is block device. But if not, like you usually access them in a byte table, then it is called character device. Okay, so character device included like the keyboard, mouse, those kind of stuff. They are all character device. So because they usually only stand in the stream, so the data transfers rate are quite low because you type on a keyboard and then you need to, for example, if you wait for several few milliseconds and you type another byte there. So usually you will not like the block device needs a super high throughput. Okay, because a block device is about you already know you want to move a super large like block. So you rely on the throughput. But character device usually is about the latency. You don't want to miss each character when you type the keyboard. So it is about the latency. Okay. So in this, I mean, in the rest of this lecture, actually, we only focus on the block device. Okay, because the storage device, those they are all block device. Okay. So block device, character device, they have their own device driver. And device driver is a computer program operating or controlling a particular type of device. Okay. Okay, so when you are using a Linux, actually, you're not really, I mean, if you are a user, not a programmer, then you will not really work with the device driver, right? But it's still possible to access, like, if you still remember like /device/SDA or like SDB or even TTY1, TTY2, actually they are all block and character device. But in the user level, you can still access them, right? And the reason is like this. So you are a user or like you are applications, and if you are going to open the file, if you are going to access some things in the block of character device, actually there is a thing called device spatial file. So device spatial file used to interact with drivers. Okay, like this. This is a user space, and then the device spatial file is /device/ like SDA-A, SDA-B, or like / like TTY1, like our monitor, TTY2, those kind of stuff. So you can think about this is an interface between the application and the kernel device driver stuff. So this kind of slash device slash SDA, if you mount the file system on it, then it will go through a virtual file system and then a driver and then to the hardware. And if there is no file system, then there is a device driver, and there's a hardware. Okay. So let me briefly recap is about kernel modules, just like device drivers, are a piece of code, so they can be loaded and unloaded from kernel on demand. So device driver, it is also a piece of code, but device driver looks a little bit different from general, I would say like OS kernel code, because it is more constructed. Their structure is quite clear here. So I'll give you an example here is a device driver. So the format here is like this. The structure here is like this. Usually you will have this kind of module init and module exit. So module init, you can think about more like when you are running a C++ code, there is a thing called constructor and destructor, right? Constructor is when you are running a C++ code, then when you first run the code, and what will the system do for you? What will the code do for you? And this is the same. When you insert a module and you run the module in the Linux kernel, it will first run the module initialization, module dash init. And in here, we will just print K to print a like kernel alert things, like hello world. Okay, so kernel runs a function when the module is loaded. It is called a initialize function, and this is using the module dash initial like function here. Okay, so the output usually is 0 if it is called successfully. And the purpose here is just to initialize hardware, allocate data structure, those kind of stuff. Okay. And then once when you are going to kill the kernel driver, kill the device driver, if you are going to unload the device driver, so you will then run the module dash exit. So the exit actually, usually people are going to free the resource, shut down, and reset the hardware. So here is about you are going to allocate your resource used by this device driver in the initialize part, and then you're going to release it in the exit part. Okay, so mainly device driver, they are composed with these two functions, initialize and exit. Okay. Oh, this is a module license. I think it's not important. Just about to let you know, you can put a license in your kernel code. Okay, so how to build a device driver? Actually, there are several ways. First of all is about to store driver code in your own Linux repository code in your offline, in your PC. For example, if you download the tarball file and if you run the tarball and then to unzip the tarball file, then there are a lot of folders. Then you can put your own driver code in the driver blocks or the driver character, depends on what kind of driver you are writing. And if you are writing a block driver code, you can put it into the drivers/block folder. Then modify the make file in the directory, and then you can run it. So there's another way, it's called build externally. So build externally is about to maintain and build kernel module outside the kernel source tree. Just like you can create a makefile by adding like 2 comments, like this kind of stuff. You can just have your own kind of .o file, and then you can compile it to the, you can have your .c file and then compile it into your kernel object file. And then you can directly build it in place. You can build it in your Linux systems, and you're finished. Okay, so for the source tree, you need to upload into the source tree, but for the build externally, you can build offline. Okay, so just to let you know, there are some different way to load the device driver. So for some cases, if you install the kernel, like kernel function, if you are going to install a new kernel object, in some cases, for example, if you change the scheduler and then the virtual memory stuff, in some cases, you need to restart the systems. But in most cases, if you are going to add the new device driver layer, in most cases, you don't really need to restart the systems here. Okay, so here are just kind of some hints to let you know what's going on for when you run the make command here. Okay. Okay, so just want to share with you some interesting when you're doing a kernel programming. So there's a question is about how to access the stat for the current process. So if you still remember, like here, we say like if you are a process, then you are running in a user mode, then it is called the normal process, right? But when this process needs the service, when it needs the always service, it dives into the kernel mode. Okay. And in this case, actually, it is about CPU to change from the user mode to kernel mode, and it still execute on the same process, right? Because it is about the kernel program they share with all the user process. I mean, the top 1 GB, if you still remember, in the 32-bit address space, the kernel space share the top 1 GB of the address space. So when you are running a kernel, it is not about you call another kernel function to run the device driver. It is about you still stay on the same user process, even the same context. But part of the context, they switch to the kernel context. So it is possible to access the current state of the current process. So what do I mean? Oh, sorry. That's just about the detail. So this is a user program process data. So the same things, this is a CPU in the user mode. And then we are going to, if we are going to access the kernel module or like the device driver in the kernel address space, it's just about for the CPU to switch to the kernel mode and then to access the kernel address space. So for the user address space part, it still stays on this user process. Okay, so it is possible for the kernel to access the stat for the current process by like this kind of stuff. If you type into print k is the print function in the kernel version. Okay, so there is a called like current current structure because it is about the text structure. So you can dot like COMM or like the PID, and then you will return the current status of the current user process. For example, what is the PID for the current process, like this. Okay. So you can get most of the information you can get in the text structures for the current process. Okay. So this is about it. And then, okay, here are several things that in the kernel functions that you need to think about twice before you are going to use them. But the first is about the super small stacks, because like when you're doing a kernel programming, actually you don't have too much of the stack size. Like there's only 1 to 2 stacks. Okay, so this is the things like if you're going to do like complex kernel code, and then you have a lot of functions to call in the kernel, probably you are out of stack. And the second one is about usually in Linux code, there is a kernel functions at a prefix, there is a double score. So this is usually low-level component should be used with cautions. So actually in kernel, there is also some are in a very low-level things. I mean, like if you accidentally modify these low-level components, maybe it will let the other kernel functions maybe hard to run or like even crash. So you can think about those are like core function that you use inside the Linux kernel. So when you are doing the kernel function programming, you can think about if you are going to really modify this kind of kernel functions in the prefix of the double scores. Okay. And I think there is a very interesting stuff is the third one. It's about do not use a floating point. And floating point support is very expensive in the kernel and should be avoided because when CPU is in the kernel mode, they cannot really use the floating point accelerators. Okay, so if you go to check in the browser to type in the Google about can I use a floating point in the kernel mode and tend to do some computations, and people will just say, if it is possible, please don't do this kind of stuff because you will be super slow. Because when the CPU is in the kernel mode, you cannot really use the floating point accelerator to do the computations. Okay. Okay, so why it is so expensive? Because it should save the floating point registers while switching from the user to kernel mode. So if you really want to use it, then there will be several hundred of seconds to do this kind of mode switching. I would say like context switching things, but the context switching is only for the floating point register. Okay. So this is about the things for the kernel programming. So I think if I remember correctly, the third hands-on will be related to this kind of kernel programming stuff. So you can just that you have a very brief feeling about how does it feel like when you are going to do a kernel programming and what can you really get after your programming. Okay, so let's move on. So after the device driver, on top of it will be the block IO layer. So block IO layer is between the file system and the device driver. So device driver, we say it is a bridge for the systems and the device. So for the IO layer, you can think about if there is a file system, it is going to access the data on the storage device, right? But actually, file systems, I mean, the file concept will be after the file system. So for this kind of device driver device, they don't really know what is a file. Okay, so we need another abstract layer called block IO layer to do the abstractions for the file system and the block device driver. Okay. Oh, sorry. Okay, so let's first do some quick background build up. So for the sector, we say the sector is the smallest addressable unit of the storage device. Okay, so if this is a storage device, then the sector is like this. So the reason to use sector is because at the very beginning, like several decades before, there is only hard disk drive, right? So hard disk drive, we said the track on each track there are several sectors. Okay, so SSD is later on, like there is a later on for the hard disk drive, but operating system is already using a sector. So from the operating system perspective, actually sector is the smallest addressable unit. Okay, so even for the OS, they send the sectors into the SSD. SSD can do the do some operations on the sector and then to rebuild it to the patch and to access it. So it doesn't really have the conflict for SSD use a patch, but hard disk drive using the sector. And the concept behind the sector is just to unify the granularity to access the storage device. Because for some storage device, they lack 512 byte. For some storage device, they lack 4 kilobyte. Okay, so the idea is just about to unify those kind of granularity. And then the second one is a block. So the block is the smallest located unit of the file systems. Because as I mentioned, file system doesn't really know like sector or like inside SSD things. So it needs another things called block. So the size between the patch, block, and sector is usually patch size is larger than block size and then larger than sector size. Okay, so sector is the smallest addressable unit. You can think about like this. And buffer is the things called like this. So it's an object which represents a block in memory. Okay, so block is the things located by a file system, right? And if we are going to use this block, it needs to move into the memory because the CPU only interact with the memory. Okay, so block is like this. When the sector is in the memory, it is called the buffer. Okay, and for data inside the memory, we need some data structure. We need some data structure to describe this kind of buffer. So there is a data structure called the buffer head. Okay, so buffer head in Linux will look like these kind of structures. Actually, there are several fields here. So for example, for the first one is about b-stat. So it is about to identify this sector inside the memory, it is dirty or not. What do I mean dirty or not? When we move a sector to the memory, and for example, when the CPU is going to update, to modify the data inside these sectors, then you will become dirty. Okay, but if the CPU doesn't really write something in its buffer, it only read it, then it will retain non-dirty. And also, it is possible to lock something in the memory. So there is about the stat for lock or not. Okay, and the second one is about a b-block device. So this one is about, because when you are going to read the sector from storage device, probably it can be from like more than one disk. It can be one from hard disk drive, another from solid state drive, another from the other hard disk drive. I mean, they can all be read from different kind of device into the memory, right? So we need some way to link between the device and this buffer. So this B dash block device, this pointer points to the corresponding block device. So for example, this buffer will be pointing to this block device, and maybe the other buffers will be pointing to other block device. Okay, so it's just going to that the operating system can find where is the data. And then there's a thing called B dash patch. So this points to the corresponding patch for storing the block. So because this buffer, you can see like this buffer is from the sector, and this is smaller than a patch. So probably this patch will comprise several buffers inside. So if the buffer is kind of 512 byte, then we can have things kind of 30, 16, oh no, add, sorry. We can have add buffers inside one patch. Okay, so we need some way to identify which patch it is. Okay. And then we have B dash data. So it points to the starting point of the block. So you can image like if we are going to access a block, the first of all is about we'll get this buffer head data structure, and we are going to find the buffer. Where is the buffer? So we'll use a B dash patch to locate where is the patch, and then use this B dash data to find out where is the starting point of the buffer inside this patch. So we can read out the data from this buffer. Okay. And also the size. I mean, it describes about how large it is for this block. Okay. But here are several challenges for using the buffer head, because buffer head is a quite old data structures in Linux. So the key thing is about buffers head plays the role of buffer to block mapping, right? So the thing is about first one is if there is a large and bulky data structure, buffer head is a larger and bulky data structure. So a block is more than a patch, and each buffer is described by a buffer head. So the thing is like if we are going to access like the continuous add blocks in one patch, then we need add buffer heads to describe this add blocks. Even they are all continuous, but we still need to access the buffer heads at times. Okay, so sorry. So each buffer head, you can think about if this is like 1 byte or even 2 bytes, then how many fields there are that you need to times like the data size, the data format for each of the field. So buffer head, it takes some place. For example, maybe one buffer head is like several 10 or even 100 of bytes here. So in this example, if we are going to access like continuous data blocks, but because one block should have one buffer head, then we need to have a large memory consumptions by using these buffer heads. Okay, so the solution for this one is in 2.6 kernel version, like kernel address space instead of blocks. So in this case, we don't really need this kind of bulky data structures. Okay, and there is a second challenge is kernel should break up large block IO operation into multiple needless buffer heads. So just as I mentioned, what IO operation is if you're going to read out a file, and this file is like 2 megabyte, sorry, if it is 2 kilobyte, for example, or even 4 kilobyte, then you need to break these 2 or 4 kilobytes or even megabyte of the operations into several buffer head, because one buffer head is only 512 bytes. So if you are going to read out 512 kilobyte, then you need 1024 buffer heads to serve for these block IO operations. So a better way is about actually we should maintain a data structure in terms of the block IO operations, not really the block, because the block is 512 bytes. Okay, so a new data structure in 2.5 is included, is called BIO. Okay, so this BIO structure is going to replace buffer heads. Okay, so this one BIO is a block IO request. Sorry, BIO is a block IO request comprise IO operation that are in flight as a list of segments. So blocks belonging to an operation need not be continuous. Okay, I think this is kind hard to understand. So here is an image here. So this figure shows the architecture of the block I/O. So one block I/O means it is one block I/O request. And for one request, actually, there are different I/O operations. So you can think about for this request, there are one read, one write, and the read and write, they are reading and writing different place of the hard disk drive, for example. So each of the I/O operations you can think about is one BIO vector. Okay, so these BIO vectors, they are chained by using the linked list. Okay, so this one, sorry, there's a typo here. This should be one block I/O request, and these are several block I/O operations here. Okay, so for what I/O operations, they interact with one thing called segment. So segment is a bunch of buffer that is continuous in memory. So because buffer is only 512 byte, but actually for patch, it is 4 kilobyte. So sometimes if you have a size between the buffer and patch, then it is hard to position, right? So for example, if you have an I/O operation, it is kind of code like 1024 bytes, then actually it means you have two buffer. But in the buffer head, you need two buffer head data structure. But in this case, you don't really need like this. If this is a patch and this is its patch frame, so the segment means any size, any continuous size inside the patch. So, but we need some way to know what is the data, where is the data. So actually, for this BIO, for each BIO vector, we have maintained 3 fields. One is about which patch it is, and where is the offset, and where is the length. So which patch it is in this patch. So this is the patch frame. And inside the patch, there's 4 kilobyte of the data. So where is the data start from? So this segment start from this offset, like this. This is the patch, and this is the offset. Okay. And with this offset, how much of the data we are going to read out? So the segment size, we can use a length to describe the segment size. Okay. So if we put it all together, so for each I/O request, it should be a continuous I/O request. And for the BIO, it can work with several I/O operations. So this I/O operation, this I/O operation, and this I/O operations, they can be combined in one BIO. And the thing is, file system will help to combine different I/O operations together and then to send as one BIO to the block layer. Okay, so here, so actually there will be a request queue for capturing this kind of block I/O requests, and it store pending block I/O requests. So requests are added to the queue by like file system, this kind of stuff, and file system will try to merge those I/O operations they are related together. For example, if these two I/O operations they are from reading the same file, like they're the same files, and then but this one we are going to read out the first part of the file, and this one maybe in the bottom of the file, but they are not continuous. So for the file system, they will merge them together and then to send into the block I/O layer with one BIO structures. So this is the things we call the block I/O request. Okay, so I think we can stop here and call it a day and see you guys next week.